All right. So what I thought we could talk about today is continue a little bit our discussion last week about path-dependent types and build a little bit into that, from that into type-level programming, where we had this kind of a little bit of discussion last week about can we use these path-dependent types to encode things like a H list, which we'll get in a second to what that is. And the answer is yes, we can. So we're going to see that a little bit. We're going to get to exercise our muscles with recursive derivation a little bit, which is something we touched on a little bit last week, but we didn't get a chance to really dig into in a meaty way. Yeah, overall, I think I'm excited to talk about this topic because I feel like this is one of those things where sometimes people kind of use this opportunity to oh, let me do this completely crazy stuff and basically be I really know stuff, and you don't know stuff so much. And we're just going to try to kind of build up from a pretty basic level and show there's nothing that needs to be scary here, of it's stuff we can all do if we put a little bit of time into it. And some of it we may not actually use most of the time, but if we ever kind of want to just spend an afternoon, it's kind of a fun little thing to spend the afternoon on, and we can kind of learn some stuff from it. So with that introduction, what we're going to try to explore today is the idea of what we could call a type level set. And so what we mean there is, if we think about a normal set, it's like a set 1, 2, 3, or it's a set atom kit. And so in these cases, each of the elements of the set have the same type. These are all ints. These are all strings. And so this you could kind of think of as it's a set of values of a given type. This is a set of ints. This is a set of strings. But the idea of one of these H things, and the H stands for heterogeneous, which is a big word, but just basically means different things, is that instead of the set or the list all being a bunch of ints or a bunch of strings, that it's different things. And we can kind of play with different syntax for it, but to kind of have a simple example, we could say we want to have some set that's basically atom, but then it's not going to be kit because these are going to be different. It's going to be the number 1, and then it's going to be true. And so this now is more what you could think of as a type level set or a type level list. And maybe depending on how we're doing this, this is going to have some final one that's it's just okay, this is the end of the list. But so now this is a list of a string, an int, and a Boolean. And the important thing about this is that it's going to actually keep all of those types. So we're going to be able to look at this and we're going to know that it has those 3 types. It's not going to be, the kind of, obviously I could always just do list atom 1 true. But if I do this, I'm just going to get a list of any here. So that's not very interesting. We want to describe something that actually is going to, in a typed way, capture these different values. And so a pretty conventional way to do this is this thing that's called an H list. And that's kind of what this would be. And so that's just the concept of it's like a normal list we know. It's just kind of this linear thing that has one thing after another, but each thing can be a value of a different type, and we kind of hold on to that type information, and we can describe different operations on it. For today, I'm going to explore a slightly different variant of that, which for this we'll call an H set. And so this is going to be kind of the name implies, whereas the H list is the type level list, the H set is going to be a type level set. And so the we'll see if we may not be able to get all of these things perfectly, but if we think about design goals, we would say, this autocomplete thing is funny. One goal would be that we should only ever be able to have one value of a, we'll call it one instance maybe, one instance of a type in the set. So for example, it should be okay for me to have one true whatever. Right now, we'll just kind of keep with the syntax. That's fine. This is okay. But I shouldn't be allowed to do something like, right, because I'm having duplicate types here. So I'm kind of violating this idea that it's like a type level set, that like a set, like you only have like one thing of that, thing. Like if it's a set of values, I only have one of the integer 1 or one of the integer 2. If it's this like type level set, I only have one int in the type level set, or I only have one string in the type level set. Second property we want to have ideally is should be commutative and associative. So ideally, again, we may not be able to do all of this, but ideally we would want to say that like 1 and true in HNL is the same as true and 1 in HNL. Now already you can see just kind of the fact that we have this like HNL thing at the end, we're going to have some challenges getting 100% there, but ideally we'd like this or something like this to be true. Some other things we'd like to be able to do, we should be able to look up a value in the set. So I should be able to do like set.getInt, and this should like, if there's an int in the set, it should like grab that and give me that value. We should be able to remove a value from the set. And we should be able to take a union of two sets. And I guess a very basic one would be we should be able to add values to the set. Let me just quickly flip over and just see if anyone has any questions here so far. Looks like we're good so far, so I'm going to keep rolling, but please jump in with questions, or also just say something to let me know that people are here and I'm not talking into empty space. So that's a little bit of what we're going to try to create. And all right, awesome. At least one person is like here. Great. And a little bit of the motivation for this beyond just, okay, this is kind of an interesting way for us to kind of learn about these like type level programming functionalities in, oh, and we got one. Let's see what the Q&A is. Is this, let's see, oops. Yeah. Can I view the Q&A? I'm having, let's see, sorry, I'm just trying to actually view the Q&A versus see that there is a Q&A. Oh, what autocomplete system am I using? Yeah, this is the GitHub Copilot thing. I think last week we mentioned it a little bit too. It's like a new thing from Microsoft and GitHub that uses like artificial intelligence. So it's kind of cool. Sometimes it's kind of silly. You know, we can probably do something like, let's see, Symposium is a set of objects that are related to each other. A misspelled Symposium is a set of tools for working with a Zymposium. So sometimes it's nonsense. A lot of times it's actually pretty good, but yeah, it's I guess a little fun thing of if you watch, you can kind of see that and decide what you think of it. So anyway, a little bit of also just the context for this is before ZLayer was developed, there was a lot of effort that went into figuring out the right way to allow people to compose the environment. because there was kind of an early period where like Zio had kind of introduced the environment type, and in a way it was like really great if it just like gave people a way to describe the dependencies of their application that like they didn't really have before, but it also created like a new set of problems that people hadn't really had to solve before, at least in a functional effects system of like, how do you kind of build and work with these more complex sets of dependencies where like just having the environment itself, it was great if you like, okay, I just have a console service or just have a logging service, but people pretty soon wanted to start to build these more complex dependency graphs where it's like, well, you know, I need a configuration information, and I use that to load a database, and then that actually goes into a like database manager that manages multiple like tenancies of these, and then this goes into some other service, and there was a demand for like more tools to be able to like add things and remove them from the environment, as well as to transform them and kind of use those things in the environment to like build more complex services. And so before ZLayer, like one of the main avenues that people explored, and this work in particular was led by Maxime Joulau, who also did the work on the profile that's going to be in Zio 2, and Peter Giebeski, I may slightly have been butchering that name, who did the work on Zio Mock and is also did some of the work on Zio microservices. They spent a bunch of time exploring this. And then we kind of ultimately went in the other direction with ZLayer, but I think this will be kind of cool of like, we'll have a little bit of like a practical use case of thinking about like, how could we use a set like this to represent the environment of an effect? And as we go through this, we'll, I think, see like some of the like benefits as well as some of the drawbacks of that. And I think that'll give us a little bit of like a cool motivating example, and also maybe some insight onto just like, you know, why we got where we got, and that whole thing. So, all right, I'm just gonna check in one more time, and then we're gonna dive into code here. All right, seems like we're good here. So with that, we're going to start by defining this trait that is an Hset. And the Hset is basically going to have two subtypes. So one, I think I'm going to call it H-empty instead of H-nil, just because it's like not actually a list, it's kind of a set we're trying to describe here. So one is this going to be this thing called H-empty. And the other is going to be, I think I'm going to do, it turns out it's kind of important for like getting the types to look okay to use this colon thing. The colon makes it right associative versus left associative. And if you don't do that, then when you have a bunch of nested types, you kind of get parentheses and parentheses and parentheses. So like the right associativity ends up being pretty important just for these like type signatures to kind of look at least relatively normal as we're doing this stuff. So I think I'm going to stick with that, but I'm going to use the like ampersand instead of like sometimes a star is used, or sometimes there's nothing, it's just like two colons. But I think I'll just kind of use that to express this idea that it's like you know, a type level anding of two things in the set versus just kind of a list. And so this, maybe we'll call it, and we're going to find here there's a little bit of a trade-off between, you know, we want this set to be this thing that is totally independent of order and all these things, but like kind of the way we have to work with like types and data structures, I mean, it's pretty hard to have like all this type level stuff is harder, and I think it'd be really, really hard to do something like a type level hash map. So we're kind of going to end up more having like our underlying representation is going to be more like a list, but we're going to implement our operations in a way where we're going to try to maintain these guarantees. So in that world, we're going to say this other case is like an anding. And so we're going to have one element that's just going to be this head. It's going to be some arbitrary type. And then we're going to have this tail that's another Hset. And so this is going to give us back an Hset. And let's just check ourselves here. Okay, awesome. And so the first thing, and maybe I'm going to give us a little just example here, just so we can kind of test some code. So the first and the most basic thing we're going to want to do is we're just going to want to have a way to construct these Hset values. And so to do that, I'm going to implement an operator on each of these things. And I think I'm just going to give it, at least initially, I mean, we could call it like include or something, but I think initially I'm going to give it kind of the same name for this like constructor as I have for this like data type here. And so we've got these two cases we got to do. So the easy one is this case where we start with an empty one. So we could say, okay, well, if you want to add on to an empty one, then we can add on this type. And this one ends up being pretty simple, that this is basically going to be the head and then this hempty thing. And so here we're just running into one, just like kind of little ergonomics thing of basically, because this is a case object, the Scala compiler, without me helping it out a little bit, it kind of has a hard time distinguishing the object from the type of that object. So if I want to make this compile, I can do this like hempty.type here, and then this will work. But this ends up being a little bit like awkward having to do this like type everywhere. So we can just fix that by doing this little type hempty equals hempty.type. And I mean, that's a little bit, I know that seems like a little bit like kind of tautologous, but it kind of helps the compiler out of saying like, okay, like I'm also going to call this type the specific type of this thing, and then I can get rid of this guy. And so this implementation is going to be really simple, that it's going to be the this little case down here, this little ampersand case with the head. And if I want to, I can just with basically hempty, or I can call this self. So I can just, maybe I'll do self here. Let's see, is it happy with that? Or, oh. And so the one thing here is I've just got a little bit of ambiguity of like, I've defined this here as a method and here as a constructor. So I can just use the package name here to disambiguate that. And now this thing will be happy. So far, if we think about like, okay, what can I like do in this world? I can do something like set is 1 and hempty. And if I look at that, it's got that. This is indeed int and hempty. So that's great. So far, so good. Now my problem right now is, ideally, I want something like this to work. And right now, this is kind of going to blow up in my face because I've only implemented this and thing for the empty case. So let's go ahead and let's implement that for the non-empty case. And I'm just going to do one more. Okay. All right. Everyone seems to be good so far. Please jump in as we're going. But OK, so right now we're said this is going to blow up in my face. So let me try to fix that. So to do that, I'm going to need to implement this same operator. Maybe I'll call this like that. Oops. So I'm going to add some new element. And so it's not quite right, but the autocomplete is not being terrible. So like the most naive way I might implement this is by saying, okay, well, I know this thing is a head and a tail. So if I'm now adding this new thing, and again, we're kind of using the head and the tail a little bit, like in terms of our implementation, that's what we're using. We're going to try to make sure that doesn't ultimately matter in how our users use it, but that's our like underlying representation. So we could say, okay, so that should be that, and then the head, and then the tail. And so let's like look at that. And so, I mean, that's right. We've captured that so far. And this we can actually implement pretty easily because we can just say, let's see, I think we can just do that. And I think we can do self here. Okay. And so this is working. And like, I think this is like a good like opportunity to just go back to this idea of like, there's not like magic here. I mean, we're definitely going to do like build up to kind of more complex things, but like already just this like simple thing that's, I mean, less than like 20 lines of code, like we've essentially implemented a type level list here, and we implement more operators on it, but like there it is, right? There you're putting these types together and you've created this data structure. And I mean, even without anything else we do, like I can just put more things into this and there they are, and they're captured at type level. So like, you know, there's not any wizardry to this. But okay, so with that, let's now kind of look at the next fly in the ointment here, you could say. So this is great. We can add things to the set. That's lovely. But think about something like this. Let's see. Oops. Close the parentheses. There we go. So, and let's see the type of this. And one of the cool things, I think that this will even. Yeah, Skeleton probably even got it there. But we see we got a problem here, because so far our encoding is basically just like a type level list, which is great. Type level list is like a great like learning thing. That's fantastic. But we said we want to do the type level set. And so if we're going to do a type level set, we can't have two strings in here. And if we go back to like that like practical example of like this being like a potential like solution for the environment in ZO, if we imagine these as like different services of like a logger and a database, like we don't want to allow there just be like two different logging services in the environment. We want to kind of say there's like only one logging service so we know which one to get. Because otherwise, if you said like, oh, log something or oh, persist something, we don't know which one to go to and it becomes kind of undefined. So we've got to somehow prevent this from occurring. This is violating the like invariance that we've set up for our system here. And so this is where we're going to go to a little bit of the path dependent types and a little bit of some of the tools that we talked about last time, because we're going to need the type of the value that we're outputting here to depend on the values that are coming in. Because like normally, you know, if I'm not trying to kind of screw myself over by like putting a second value of type in, normally if I've like got a like true and a 1 and I add an atom, then I just need to like add that new type to the beginning of the rest of these types. But if I'm trying to add a type that I've already got, then I need to know that I basically need to like kick that type out. And I can either have semantics of kind of the old one wins or the new one wins, but there's definitely only got to be one at the end of the day. And I've also got to be able to handle this like this in a way is maybe the simplest case where these are just like one after the other, but I've got to be able to handle the case where maybe the duplicate type is in here. And I've still got to make sure that, I'm not sure, oh, this is just not matching up again. Now I got to regenerate this type. Yeah, so whether I added next to each other or not, I've got to make sure that like I don't allow this situation to exist. And so this is a great use for path-dependent types where we have this idea that we want the output type to depend on the specific input types. And so to do that, I'm gonna create a new, generally the pattern we follow is we're gonna create like a trait that's gonna kind of describe like the logic or like the type level function we want to apply. And then we'll kind of create instances of that trait that are going to describe the particular ways we want to handle particular inputs and turn them into outputs. So in this case, we're going to I'm just going to call this eliminate. And so then we want to think about this. It's like a type level function. So we got to think like what types need to go in and what types need to come out. And so this basically, I think we're going to need two inputs. So essentially, we're going to need a target type, let's call it, or maybe we'll call it an element. And this is the type that we want to eliminate. So this is like eliminate, make sure there are no instances of string in this thing. And then set is going to be the Hset that we want to eliminate from. And then when we're using these kind of type level functions, we're going to have one, maybe more than one, but typically one type here that's going to be like the output of that function. And so this type out is going to represent the set with elements eliminated. So just to kind of, so element is equal to type to eliminate from set. Set is equal to original set before elimination, and out is equal to resulting set after elimination. And so to give ourselves some example of the expected behavior, we would say, sorry if there's some background noise. I think there's some kind of traffic thing going outside. So we would say like eliminate. Oh, hello.
Hello.
We got Kit in the house. Yeah. Party time. All right. Hold on one sec, folks. Let me get Kit an invite here for the. Oh, maybe I don't even need to navigate away.
I'll be the spell checker. The spell checker has
No, you are the best co-pilot.
Oh, you're using co-pilot.
That does not even do you justice. I know. Well, sometimes I'm your co-pilot. Let me. I think I will just do it on Discord since I'm already here. Hold on a sec.
Yeah, it's like the post office, rain or shine, sleet or snow.
Yeah.
Got a Symposium. Thank you so much.
Yeah, definitely. Yeah, so I guess and we've also got a question here, maybe. Let me see if I can go over and see the question. I'm not, for some reason, I'm having a hard time seeing. Here it is. Oh, I think it was just, I think I already did answer that one. Let's see. Yeah, I think that was one I already answered. Okay, sorry about that. So basically, we talked about the concept of the Hset. We talked about some properties we wanted to try to achieve, may not be able to achieve them. We talked about the idea that this was kind of an alternative for Zio's environment type. And we did like a very basic implementation of constructors, but we noticed this issue that we could kind of add duplicate values to our type level set, which violated one of the invariants we wanted to maintain. So we were just working through an implementation to deal with that.
Nice.
So yeah, so we said we're going to implement this eliminate thing that's basically going to like describe the logic for how we're going to eliminate a type from the list. So this is going to be a type to eliminate. This is going to be the original type level set. And this is going to be the set where we've removed that thing. And so if we like eliminate int from int string empty, that should equal string empty. And if we eliminate int from, let's just call it string and boolean and hempty, then we should still get the string and the boolean and the hempty. So basically just remove that thing. And so we've got our basic logic here so we've got the two inputs, we've got the output, and then typically you're going to also want some type of function that kind of embodies that logic at the value level. So like here, I think we can say, if we're eliminating this thing, then we should be able to take a set in that's of the original type, and we should get a new set out that's got that eliminated. And so even before I kind of do this, one of the ways I can check my logic here. Oh, I just needed this name, sorry. Eliminate. Yeah. So one way I can just check my logic here kind of even before having the instances is I can think about how would having this thing let me implement these signatures better. And so if we go back to these signatures here, this one is really okay because I'm starting with an empty set. And so I can't have a duplicate from the empty set. So anything I add here is fine and I can just move on with my life. It's really here that like this problem arises because I can try to add a string to a set that already has a string in it. And so what we're going to do here is we're going to change this from returning a specific type to we're going to have it take an implicit eliminate that knows how to eliminate that from this set of head and tail. And then now it's not going to, we're not going to be able to know just in general what that type is going to be because we don't know if we're actually eliminating something or not. We don't know if we have a duplicate. So instead, the output type is just going to become whatever this eliminate thing says it is. And now, of course, this is going to change. And so here, we should now be able to, so basically we're always going to, at least in this world, we're always going to add this new value. And then we're just going to kick out whatever old value is like the value of that type. So I think this thing of like anding on is right. We basically just need to take the original thing and we need to call eliminate on it. And let's see what we've got here. Oh, and yeah, Kit is pointing me to the fact that based on that logic, we're always adding that. And then this eliminate is giving us the rest of it. Okay. And so now that's happy here. But now, of course, if I try to uncomment this, I'm still going to have a problem because it says, I don't know how to eliminate anything. You kind of described this like conceptual idea of eliminating things, but you didn't actually describe how to do that. And so that's like the next thing we're going to do. So once we implement one of these traits, the next step is we want to implement some instances of that. And we're going to want to end up making them implicitly available, just like we implicitly asked for them here, so that they're just kind of automatically created and the user doesn't actually have to deal with them. And a lot of times what we want to do is we want to try to start with like the base cases of like what are the simplest cases. And then we want to go have some recursive cases that are going to try to like make the problem simpler. So it's kind of like if we worked with a list and we just said, okay, well, we're mapping, we're going to map the first value and then we're going to go on and we're going to map the rest of them. But since in the type level, everything is like a little bit more complicated, but we will still work through it. But first, it seems like we have a question, so we will check for the question. Can the compiler infer the type of and in this case? So once it is not blowing up, it will infer the type of and we will see that shortly. So in this case, kind of the easiest case you could say is maybe we call this like empty. And we would just say that if you're trying to eliminate something from the empty set, then you're done. You can just return the empty set because no matter what that value is, you can always, it's already eliminated. It's kind of done for you. So we could say this is going to take a head, and sorry, I'm going to. Sorry, what's that?
No, I'm just impressed that it seems to be correct, or sort of.
Oh, yeah. Yeah. So, but this is reminding me that I need one more trick here, which is to be able to actually use this out type in other places. I'm going to need to use that pattern we looked at last week, which is sometimes called the aux pattern, but this is another where like I feel like it's way nicer when you do it this way. So we're going to say eliminate with the output type is going to be, so this is going to take an element. It's going to take the set, subtype of the Hset. It's going to take a out. Oops. Yeah, an out 0.
Try to sneak in there,
yeah. Avoid naming conflicts here. That is also going to be a subtype of an Hset. And this is just going to be an eliminate element set type out equals out 0. Okay. And then I think we should be good except for, yeah, this. Okay. So this empty thing is going to say, given a head, I can give you an eliminate without that knows how to eliminate the head from the empty set and is going to produce an empty set. And sometimes here, you can kind of go either way. You can either just implement them as you go. Sometimes I find it's actually easiest to just kind of implement like the type signatures before I even implement the implementations, because sometimes you need to play with the type signatures a little bit to get them to work, and that'll kind of make sure that you get everything to work. And we will actually be able to get to the point where like this will like look fine and this will work, even though we haven't implemented these question marks yet. And then it's usually the value part is like the easy part compared to like the type level part. So that's one case. So the other case you can think of as kind of the recursive one. So we could say something like maybe this one we call eliminate. And so this is going to take a head and a tail that's also an Hset. And this is going to, and this one will be a little more work, so I'll kind of work through this. So we're always going to want to use this eliminate without thing. And so this is going to say, if I'm trying to eliminate the head from a Hset that has a head of the same type and something else, then the result is just going to be the tail, right? So if I see, you know, int string empty, and I'm trying to eliminate int, then my answer is string empty, and I'm done after that. And one thing that makes this case a little bit simpler here, the way we're constructing this, is we're saying we're only ever going to allow there to be one value of a type in the set. And so as soon as we find one thing to eliminate, we're done, because we're adding one thing, we've eliminated one thing, so we've maintained that invariant. So if we wanted to do something like eliminating and we had kind of more, we had the possibility of more instances of the type, then we might need to like further recurse to like get all of them. But since we're maintaining this invariant that we're only ever going to allow one thing to be in there, once we've eliminated that one thing, we can just be done. And then the final case we have to deal with, so we've said kind of I'm empty, I'm not empty, but I have two matching types. So the final one would be I'm not empty, but the types don't match. So let's, maybe I'll call this like recurse. And so here I'll have, maybe I'll call this like element, a head, and a tail. And this tail is also an Hset. And so this one says, I'm trying to eliminate this element. And I'm trying to eliminate it from this set here. So I'm trying to eliminate it from head and tail. But now we've got a little bit of, I'm just gonna put nothing here for a sec, just to kind of highlight this problem we have right now of, I'm not really quite sure what the output type is gonna be. Because at this point I've said, okay, the head is not this like target type for elimination. So the head's okay. So it seems like I want to do head and something, but I don't really know the type of the something yet, because I don't know if the something is like just okay and I can just return the whole tail as is, or if it itself contains this target element somewhere and I need to eliminate that. So that's where this like recursive thing is going to come in. And so we're going to say in this case, we're going to need another eliminate. And this eliminate is going to know how to eliminate this element. But now, instead of knowing how to eliminate it from the head and the tail, it's just going to know how to eliminate it from the tail. And so then I can replace this nothing type with the eliminate.out. And did I just?
Oh, this is capital O.
Yeah, I thought it might be something silly like that. Okay. And so the one other thing you have to watch out here is sometimes you can need to use that prioritized implicits trick. So like I think we may need to move this recurse one into a low priority instance, but let's just like try it for a sec without that. Let's see what we got here. Yeah, I think we need to move this one here, I believe. Let's see, is that working? Could not find. Oh, yeah, that would be good. Okay, and now I think I just need to regenerate my type signature, which I can now not do quite as nicely as Kit can. And we get a little bit of this weird, I'm not quite sure why VS Code does this, does that, but I mean, that's kind of a VS Code thing. We can see that now when we did this, we got the right type. We eliminated one of those strings. Now there's a little bit of like a weirdness here of like, you know, right now I think we probably did the most logical thing if we like put the string at the beginning for the one we added and then we eliminated the one from the middle. I think as far as our like design goals go, it would have been equally fine for us to kind of do it the other way around. Hopefully we'll try to a little bit later on get to a way to make that just not matter as much. But I think with the caveat that none of these are implemented yet, which we'll do in a second, this is pretty cool here, right? That we've had a way to combine these things and preserve their type information. And we've now maintained this new like invariant that like we can't add duplicate types to this set, which seemed kind of complicated to do in this like type world. So let's go through and let's implement these instances, and then maybe we can just do like a little check-in for questions, and we'll go on. So each of these, we just basically implement the signature here. And a lot of these, as we see, will end up being like pretty trivial. So like this says like, hey, let me just put in, we do need to specify these out types here. So here like type out is h-empty. And so this is like, hey, given an empty set, return an empty set. Well, that's really easy. Set. Mission accomplished, other than I think we may have extra brace somewhere. I think we're just in the process of doing this.
Mm-hmm. Oh, I'll let you do it. I was just playing around. I got Copilot myself, so I'm excited.
Oh, nice. You're piloting, awesome.
Yeah.
Let's see, head tail. Okay, so yeah, we usually need to specify this. Okay, and let's see. Yeah, so this is going to be a head and tail. And so this one, we're eliminating it. so I think we can just do set.tail, I believe. Let's see. Yeah, I think we're just getting compilation errors because we're kind of mid-typing here. Let's just see. Yeah.
Nice. And this one would be type out equals eliminates dot outs, right? Oops, I don't even know. It's eliminates. Does it know? Takes a second to fire. That's fine. And then I'll copy def apply set head tables.
And I think we need a head and eliminate dot out.
Oh yes, of course, of course. Okay, cool.
Okay, and let's go back and check in ourselves. Okay, let's see. So, oh, and then this is going to be head and eliminate out, I believe. Yep. Okay. So now, all right. So our types are happy. So we just got to implement this thing. And this is also end up being pretty simple because we can just do the Hset. And then we've, so this is the one where we just want to keep going here. So I think we can do set.head and then eliminate set.tail. I think I have one extra parentheses. And there we go. So like, I would say like first, like, relatively like definitely non-trivial type level function implemented here. And there's definitely a little bit of like a pattern to it that is maybe not a pattern you would use before. Maybe if you were like doing kind of type classes and you were like inductively deriving type classes, you would have done a little bit, but not really crazy when you break it down here. We just wrote this trait to describe this essentially function we want to have that says like, okay, give me an element and give me a set you want to eliminate the element from, and I'll give you some output. And then we just implemented these instances that describe the different steps we wanted to take to apply that logic. So yeah, let me just quickly.
We've got two questions.
Yes. So okay, one about why have both eliminate and recurse? Why not just eliminate that removes wherever it finds the type? I think we could potentially do that. Here it seems like, one, this just might be a little bit more efficient of like once we eliminate once, we know we don't need to recurse because of the invariance we're maintaining, we know that there's not another instance once we eliminate the first one. Sometimes, and we'll see this maybe a little bit later, but one thing we have to be careful of that we can sometimes run into is if we have more than one of these implicits that we're relying on, we can't use the out type of one of them in the other. So sometimes we need to be careful about kind of creating a situation where like the result of one type is going to like change the other. I think we could probably get around that here, but partly this just seemed, again, simpler of like, once we do one, we're done. Yeah, so I think you might be able to implement it the other way too. That's just kind of the way I thought about implementing it. Okay, so if we go back to some of our design goals here.
There's one more question.
Oh, yeah.
Which was,
sorry, maybe I missed it, or maybe it was, yeah, go ahead.
Which is, yeah, would it eliminate duplicates of parameterized types as well? So like list of one. And
oh, that's an interesting test. Yeah, let's try that. So let's say val set1 is equal to list one list Adam. Yeah, I'm not quite sure how I was going to handle this. So let's see. Okay, and looks like these types are sticking around, which makes sense that we haven't really used any variants here. Let's just, maybe I'll do a little, oh, right, we can test that one too. Yeah, let's let me undo this so we get the autocomplete. Yeah, that's a good test here. So yeah, it looks like we are successfully eliminating them, modulo kind of VS Code telling us unnecessary information. So yeah, I guess depending on your use case, it could be good or bad. I think that's generally the behavior we want. So yeah, cool.
Yeah, and that's because these in Scala, you basically have to, when you have these type variables, you annotate them with their kind. I don't know if we've really talked about kinds yet. Obviously, we use them, but like list by itself has an argument, right? And so if we wanted to reference, if element wanted to have a type, sorry, if we wanted element to be something like list with an unapplied argument, we'd actually have to add that little annotation there, which is not what we want to do. So we're just using fully applied types. So element, head, tail, these type variables that don't have little brackets and underscores. These are sort of like, these are the types that can be represented as values. And therefore a list of ints is totally different than a list of strings. And yeah, they're not going to step on each other's toes.
Yeah, and some of these, it could be interesting to explore. Like we've generally avoided using variants on like either these like traits here or the Hset itself. I think if we did, that might result in possibly different treatment in some situations. So that's another thing we could kind of look at. But I think we probably got enough complexity going on here. We'll stick with the invariants on those for now. So going back to the design goals we had here. So one of them is we should be able to add values to set, which ended up being the last one on the list, but it's kind of an important one. So I think now we can say check, if I can spell check, there we go. So we want to be able to do union, which we definitely don't have yet. Want to be able to look up and remove. We've kind of, I think, basically done at this point. I mean, we're kind of primarily using it right now as kind of a way to implement adding and maintaining the invariants, but I think we've basically implemented that. And we'll have to keep working at this as we implement other operators, but we've so far maintained this invariant that we can only ever have one instance of one of these types. So I think maybe the next interesting place for us to go would be this lookup, because we have ways to put things in here, at least one at a time. Maybe we can work on putting groups of things in, but we have ways to put things in. We don't really have a good way to get things out, at least a way that respects the idea that this is a like set. Like we could definitely like just like treat this as an ordinary data type and kind of deconstruct it, but like the whole idea of being a set is that like the order shouldn't matter. So why don't we tackle that? And so for that, I'm going to implement a method here that I'll call get. And so, well, I'm not even going to implement it here because the first thing we can say is that it does not even make sense to try to get a empty value from a type level set, because since it's a type level set, you know at compile time all the values in there and you know there's no value in there. So there's no point in trying to get a value there. But if you've got a set that has some elements in there, then it could definitely make sense to get a value out of there. And so we'll say get, and maybe I'll call this like an element type. And one of the interesting kind of implications of this being a type level get set is that like, there's not, all I have to do is I specify the type, right? Like for a normal, if I had like set 1, 2, 3, it'd be like apply to or contains to. I would kind of give it an argument. And here, I mean, I'm giving it an argument, but in a different way. I'm giving it a type level argument. I'm giving it like, here's the type of the element I want to get. This is another place that we're probably going to want some of that to use some type of implicit value here, because this could be, right, this could be a valid thing to do, or it could not be a valid thing to do. If I want to say, get an int on a set that contains an int, then that's great. If I want to get an int on a set that only contains a Boolean and a string, then that shouldn't even compile, because we know that like those types just aren't there. So again, I'm going to need a implicit, and I'm going to follow a little bit of a similar pattern of like kind of a good strategy a lot of times is kind of just make an implicit that like start by just like having the word describe what you wanted to do. So I think in this case, I'm going to call this includes. And so includes is going to take one argument that's like the type that I want to look up, and another that's the set that I want to look in. And it's going to have an output type. This time it's not going to be a set because it's just going to be that value. And so basically, if I apply it to a set, if there is an includes, an implicit trait. I'm not sure why I'm making that implicit. Sorry. So if there's a includes for this element in the set, then that means I can actually take that set and I can get that element out of it. And so, yeah, I don't think I actually even need this here for this one. So this is like a little bit of like, you know, again, sometimes we need like the path dependent type thing. Sometimes we just need like the evidence to prove things. So this is more in the like just proving things category. And so I've implemented this. I think Kit is probably already above. Yep. So now we're requiring that implicit includes. And then we've got the nice method implemented. So we just apply it there. And so, I mean, again, kind of just going in this nice like iterative fashion, we can already say like val my string is equal to set dot get string. Let's see. Oh, right, we don't have the instance yet. Sorry, I should actually wait till we have some instances. All right, I jumped the gun a little bit there, but that is all good. So I think Kit is already going in exactly the right direction. So first kind of, now the one thing that's a little bit interesting here is for the eliminate, one of the properties we wanted to have was we wanted to say that there's essentially always a way to eliminate. This thing is telling us how to eliminate, but there's always some way to eliminate. Maybe it's by giving you the same thing back. Maybe it's by giving you something else back. But essentially, if you give me like a value in a list, I can always give you back an eliminate. This includes is going to be a little bit different in that an includes isn't always going to exist. If I look for an includes of an int in a set that just has a string, there's just not going to be an includes at all. So I think that this case is actually basically not going to be defined for that reason, that like if I have an empty set, like I'm not able to get an element out of it. So I think I'm going to comment that out, and we'll kind of see where we get with that. So then this includes case is going to be a little bit similar to like the eliminate case here. So I could say if I've got a head and I've got a tail that's an H set, then I've got, oh, and let me again do my little, oh, I don't even need that without check on this one. So if I've got a head and I've got a tail, then I've got an instance for an includes for the head and the tail, right? So this just says like, if I've got a head and a tail and I'm looking for the head, then check, mission accomplished here. And then the recursive case, yeah, exactly, I'm already going there, would say that if that's not true, right? So this failed because we're putting this in low priority. If that's not true, then I should see if I can find it in the tail here. So we could require an implicit includes, where we're now going to look for the element in the tail. And now that we've done this, I should now be able to get this to work. So now, if I do get string, that's a string, and I know it's a string. And if I do, let's say my double equals set.get double, then I get a compilation error. And if I want to, I can even, let me do a little
I was just going
import
to mention
here.
that. Yeah, that's it's super nice to have
Yeah,
that.
yeah. So I'm going to import this cool thing called scala.annotation.implicit.not-found. And that lets me add a little annotation here, as the name would imply. And I get to just write some text. And I also get to actually reference these variables within this text, and like the compiler will like put in the actual values for them. So I could say something here, and I think it's basically, it's like a dollar bracket. So it's like dollar element was not in dollar set. And let's try that. Compile again. Double was not in string boolean in empty.
And you want to make sure you don't do the S here, even though it looks almost like the string.
Yeah, that will not give you a good time. Yeah. So yeah, so that's I mean, again, like pretty kind of cool. So we'll comment that out since it's not compiling. And maybe we'll do one more check-in for questions here.
I
think we're good so far. Okay, awesome. All right, so then going back to our checklist here, we said we should be able to look up a value in the set, check. So we've got basic. Oh, yes. So yeah, it's funny because once you do this a little bit, like the type level part is like so much like the harder part that like you can almost like forget about this. So yeah, so element head tail. And yeah, so Kit did the first one, which is like super almost like trivially simple of like if the head's the right type, then I can just return it. And then for this one here, so if and I think oh no, I won't need that. So here I'm just going to we don't need. I know I keep doing the same thing too. So here we can just call includes, I think, on the set tail, and there we go.
Nice.
So again, like the complexity here is like dramatically more kind of just like figuring out like one, just like knowing the pattern, which like is a little bit different, but is actually not like that complex when you like have done it a few times, and then just sometimes figuring out the right like logic to do this recursive derivation.
Could I actually write something out really quick just to sort of compare?
Yeah.
Useful to compare like a value level. So let's like do include value, right, for a list, right? So you have a list of A, you're going to take a value of A, and you're going to take some list. That's a list of A, and you want to get that at A out. Obviously, this has to be an option. The magic of the type level is that it doesn't have to be. Let's just blow up in that case, just to show off that how the type level like allows you to implement these partial functions safely. Using the knowledge of the types that they have. So here, it's very similar to this match statement. We have this inductive data type, this recursive data type, a list, and we want to match on it, right? And if it's nil, which, well, actually, that's the case that we decidedly did not handle right here, right? So instead, we have these two cases. We deleted the empty case. So here we have if head is equal to value, then we want to return head. Otherwise, we want to head tail call on the list, we want to recurse, includes value with the same value and then the tail. And so this pretty much is the value level version of our method above. And it's partial, we get a little warning here, but that's the beauty of it being at the type level, is that it knows by implicit resolution whether or not it can call this function at compile time. And we don't have to say like throw an error here. The compile error.
Well,
oh no.
Well, yeah, and I mean, I think you can even take that analogy here of like making an implicit not be available is essentially the compiler, the type level version of throwing the error. And like, fortunately, it's like much nicer because your code just doesn't compile and you can fix it. But like those are kind of, I think, the corresponding, you could say, ways at the, like the type and the value level of just saying like, I can't handle this. This thing is not supported. I have no way of actually giving you what you're asking for here.
Yeah, let me make it exactly like the same. So this is kind of exactly what we have. And so the recursive case, where it requires this inductive, recursive version of the type class, the way that we're sort of writing these methods, this just calls itself recursively. So it's very much a one-to-one mapping. And if you can sort of write something, if you have a good sense of writing recursive functions on some inductive data types like lists, chances are you can lift all of those sorts of functions to the type level and do all sorts of other fun things too. Like the same intuitions apply, and it becomes pretty nice. The syntax is a lot scarier looking, but as you could tell by us, like sort of like typing things we don't even need, it becomes reflexive, right? We kept putting the out without, because like mostly the same pattern. And this is a slight deviation in that we don't need, this does not, we're not deriving the output type at compile time. We're just using the knowledge of the structure to implement it in some special way. But yeah, so that might be helpful.
Yeah, I think that's super helpful. And I think it's also a nice thing because, like, at least I find a lot of times I just like try to kind of go directly to implementing it. But I think especially like either if you're starting out or if you're like kind of struggling with one, probably actually implementing it kind of explicitly at like the value level and then like kind of trying to like translate could be like a nice way to like unbottleneck yourself. So I think that's really good.
Yeah, well, and like in this version where we have to match at the value level, matching at the type level involves this other sort of variant where you like, it's kind of, it feels like pattern matching in some weird little way. It's this type level pattern matching. It takes some getting used to. You kind of have to like reverse your brain.
Yeah, and it might be interesting at some point to maybe when Scala 3 is a little more mature, we could kind of do an exploration of like how much of this we could do with match types. Because I think some of this is like, we're kind of doing this like very fancy like logic programming type of thing because we like don't have like direct like language support for it, but Scala's a very flexible language, so we're kind of still finding ways to do it. So yeah, that could be fun to explore.
Very much.
Okay. So going back to our checklist here, we've done most of these things. There are kind of two things left. So one is union, which is kind of probably going to be a more complex version of the like adding a single value, because we got to like add all the values and we got to maintain this like invariant. We don't add the duplicates. So that's one thing we can work on. And then the other thing that I guess is pretty important from just a like overall like assessment of like how do we feel about this whole thing is this idea of being commutative and associative. And so if we think about like the environment type in Zio, one of the properties we get is that if we have something like has logging with has database with has monitoring, I can rewrite that all day long as much as I want in any order I want. I can change that to has database with has monitoring with has logging. I can even add duplicates. Like these two things are the same. And if I wanted to, I could like with has database again. Like doesn't matter if you say like you need the same thing twice. That's just like an identity. And that just works like totally naturally with has. I can switch the order around. There's really not even a concept of like order of operations. I can have duplicates of something, it doesn't matter. So that's like a really like nice experience. And it makes sense because if we compose an effect that needs the database, another effect that needs like the logging service, like we need both of them. There's not really a meaningful like ordering between the two of them. And like if we, depending on the order in which we combine the two effects, if we do like, get database, zip log something or log something, zip database, we could kind of end up with those two in like different orders in different parts of our code. And if those two things ended up being different, that would be really annoying. And I'm not sure how people even like think to deal with that. And so one of the disadvantages of what we've got so far is functionally the order doesn't really matter. Of like we saw like we can get this thing, and whether it's the first or the last thing in kind of our underlying representation, we'll still get it. So in terms of the actual operations we support, we're like pretty good on this so far. But in terms of like Scala's type system, like we even saw this a little bit before. So like we saw, okay, we get this nice reduction, but if I try to type this as like Boolean string int, this is going to give me a compilation error. And again, kind of going back to the idea that like it's a list. I mean, if the underlying representation is a list, it makes sense. But I think that's sometimes one of the limitations of being at the type level is that when you're at the value level, you can kind of hide the underlying nature of the values from kind of the values you expose. So like if you think about like a set, like it's probably like some kind of hash set that like has some like array underlying it somewhere that like definitely has an order to it. And like sometimes you can even see that of like if you like iterate over it, you like have to iterate in some order and you're going to see some particular order. But you can kind of hide that in most cases of like, well, you make the array private and you make it a set and you only have these operations. That tends to get more challenging at the type level because all these computations are based on these types. And if the types aren't available, if like, we just give you like an H list or an H set instead of telling you that it's this specific H set, we're not going to be able to do any of these like fancy computations we've had above. So I think this ends up being like a fairly like fundamental problem. And, if you think about like good and bad things about this, like, I don't think there's just like a solution for it. I think it is like one of the like, design trade-offs of like going this way versus something like has. There's actually, I think, a little bit we can do to address it. So I'm gonna like, let's just like explore something here with this. So
just real quick, just before, because there was one last question.
Oh yeah.
On the last thing.
Oh yeah, please.
It was asked, can you explain how implicit not found works in line 82? One implicit value is not being matched here. I don't see any implicit in the body of the include.
Oh yeah. Yep. Let me go back to that. And let me undo my little thing here, I guess. Okay. So let's make that happen again. So we got this error. We said double was not in string Boolean int, and that's because get takes an implicit includes. Yes. And we weren't able to find the implicit includes because we made sure to set it up in a way that like it never existed.
Yeah, so the interesting thing is, even if you look, can you scroll to the body of the trait? Yeah, there. So it's not so much that this error will fire internally in includes. Includes, you're right, does not have any implicit requirements, and like def apply doesn't take an implicit. It's when includes is used implicitly, it will then use the error you specify here, which is kind of nice. It can be a useful thing if you're making a library and you want nice error messages. But it's kind of the way around.
Yeah, and I mean, it may be easier to like think about it in like a simpler example of like if you had like a type class of something of like, if you say like trait equal. And so, this could just basically know how to compare two values of type A for equality. And so you could have a implicit not found that's like, no implicit equal defined for A, and then you could define equality for like ints and strings and other types, but you could say, well, there are some types that don't support equality, like functions. And then if you accidentally try to compare two functions or two unrelated types, you would get some error message that would say no, implicit equals defined for any or for function 2. So that's that pattern. And it's definitely anytime you're defining your own thing that is going to be available implicitly, I think it's probably, I think in almost every case, it's really nice to do this and try to have at least some specific error message. And then sometimes it can even be worth having in kind of creating your own implicit traits just to get that error message. So like in Zio, Kit actually implemented kind of specialized variants of like the is subtype of, where like normally if you like do the is subtype of is like this just like arrow colon arrow, and if it's not there, it's just like, no implicit arrow colon arrow found. But he implemented specialized variants for the error type and the value type. And so then it like says something more specific, like this operator requires that the error type be a subtype of X, but it was actually Y, which, again, if we're kind of not like, deep into kind of doing this stuff, is like way nicer for the average developer.
Cool. Yeah, I think that's, this error is actually being thrown online or fired. That implicit error is on line 41. That's where it's being, when we're calling, because we're calling get, and that has the implicit lookup, and that's what's not failing down there. So it's
exactly.
Yep. But yeah, good question, because that could be tricky.
Yeah, great question.
There's a lot of like little mechanisms of Scala that are interweaving
Yeah,
stuff, like all these little tricks.
totally.
It's very much a hack. It's very much a pyramid of hacks. That happens to be pretty cool.
Yep. Okay, so let's hit a little bit on this idea of the commutativity and associativity, and then we'll do the union thing. So I don't think there's like a full solution for this. One thing that we can play with a little bit is actually based on this get thing. And so like, let's think about just like this case here where we basically want to like, we want this to work when we switch around the order here. And so let's try something like this first. So let's call this maybe identity. And this will take three things, A, B, C. And it's also going to take some set. And
type of Hset? Should I make that?
yeah, that would be great. And so this is going to say, well, if you give me a set that's one of these Hsets, and let's say that you give me a bunch of evidence. Let's say you give me evidence that A is in the set. And you give me evidence that B is in the set. And you give me evidence that C is in the set. Then I can give you a and a B and a C and an empty. And oh, I think I just need to call this up as 3. Okay. And we'll come back and implement this in a sec, but we can kind of see how, like, I mean, well, it's actually really going to be pretty trivial because each of these things already says we can grab those things from the set. So we'll basically just grab them. And so we can imagine if we had that, then let me do, so now let me say, I want to give this a different type. So this is still going to blow up on me for the same reasons. But now, if this is working, I should be able to call identity on this thing. And I think it should. Let's see.
It's in an object, I think.
Oh, yeah. So I can do
it's
Hset.identity. Right. That's oh, is it where we
you put it on this?
That was silly of me. I should create an object for it. Yep. Perfect. Okay.
Oh wait, we need that. Okay. And then.
So now, yeah, perfect. Okay, and I think this. Yeah. Nice. So this is okay now. And then we can actually take this even one step farther. We're going to use a little bit of black magic. And oh, not there, but there. I can make this implicit. And so this is what we call like an implicit conversion. So like we're seeing, like I'm getting a little thing of like squiggly saying I should do this this specific import to like show that like I know what I'm doing and I really want to do this. So you know, this is not without trade-offs, but let's kind of try this. This is about language, I think. Versions. So now that'll be happy. And now I can get rid of that Hset.identity. I think we can just get rid of, yeah, perfect. And now this will just work. So this is a little bit of like, you could call like a poor man's associativity identity of like, yeah, like this is pretty cool. Like I was just able to like assign this to like a arbitrary order and this kind of works. And you know, right now this is a little bit specialized for the like 3 case, but you can imagine, you know, I can call this like identity 3 and I can go all the way from 2 to 22 and we can kind of make this feel very associative and commutative. I have a feeling that there would be some like more advanced type inference cases where like that's going to kind of fall down a little bit relative to like things literally being identical. But it's not bad for trying to address that problem, at least in kind of day-to-day use.
Yeah, I wonder if potentially actually we could turn that into a trait, one of these implementations, right? This isomorphism or identity, this Hset identity, sort of one of these type level methods. And then you could use it both as an implicit conversion, but also to actually transform these types of one another.
Yeah.
Entity.
Yeah, I mean, it's like once you start thinking this way, then you kind of think about a lot of interesting things, like what would a type level subset function look like? Of like, you give me two subsets, like tell me if their one thing is a like proper subset of the other. There are a lot of like fun things you can do with this. But anyway, I don't think that like fully solves the problem, but like I thought that was kind of a cool thing as I was like playing with this.
That could be, I mean, that could be interesting. I mean, I think we've talked before, maybe not on here, but how, like the has type, which Zio currently uses, which is very, very cool. And there's a video from a while ago called like I can has or something.
And so can you.
So can you on our little Zyverge channel about that, which is cool, but different, very different than its implementation. It's not using these exactly this flavor of type level trickery. It's using something different. But it is potentially more hacky than this, depending on how you look at it. Like if it might be an interesting thing to explore, but there definitely are like trade-offs because you have this empty type everywhere and different things like that.
Yeah, and I mean that's part of why I thought this was like interesting to explore, and maybe a little bit interesting than just kind of doing the H list again. Is like, yeah, I think it does have a little bit of that practical implication, and we've been mostly focusing on kind of this and like the issues with it, but we could, as you said, like we could kind of say things about like the has, that it kind of relies on these tag things, and depending on like, especially early on with Scala 3, like those were not always available, and that like has its own quirks. So I don't think there's anything that's perfect. And yeah, I think a lot of this is just like gives us a nice chance to kind of explore a alternative to it and kind of see what we think. So I think I think this maybe we'll say like half check here or something of like, I think we've made a pretty good effort at that. So I think our final thing we'll try to hit on is the union of two sets. And if we can do that, then I think we'll have enough infrastructure where we could like play at least in like a toy example with like what this would look like as like the representation of the environment type. Because like when we combine two different like Zio effects, we need a union of like the two different dependencies they have. So it's great that we can add them one at a time, but we need to really be able to add groups of them to do that. So we're going to proceed much the same way we have with everything else. We'll start by just defining a type. And so here we'll union with some other thing that is going to have to be an Hset. And again, we can kind of start with like almost it's not in the standard library, but I feel like it's kind of a good one that like I think John does sometimes, is this like type question equals nothing. We can already use the question at like the value level to be like not implemented, but I do think it's kind of nice here when you're kind of doing this stuff here, because again, you just get to like, I'm not sure what this should be yet. And so this is another one where like, if we think about it a minute, we like pretty quickly realize we're going to need another one of these like type level functions, because when we do the union, what type we get out is going to depend on what overlaps there are, because we've got to maintain this property that like there aren't any overlapping types. And this in a way is going to be even more complicated than the example just adding one, because we've now got these like that we've got potentially got more than one overlap. So we're going to have to solve a little bit of like the problem that got raised earlier about like doing more than one removal as well, and at the same time as we're like combining all these values. Okay, so we've got this union here. Actually, one like really simple thing we can do just to kind of knock out is just like the kind of adding one case with an empty was really simple. The union case here is going to be really simple. We're basically just going to ignore ourselves and we're going to return that. So that's very simple. And now Kit has done exactly the right thing of going ahead and sometimes I've kind of given these different names I felt like are more logical, but another like nice approach, and I mean I think it's the logical name here anyway, is just kind of use the name of the method you're like trying to support for like the name of the trait you define. So I think union is a fantastic name here. So we'll do trait union. And so again, like thinking about this as a function, this is going to have to take these two Hsets that we want to compute the union of, and then it's going to give us a new Hset back. And thinking about like the actual function we're going to need, it's basically just going to take those and give us an out. And then we can kind of check that if we want by this time. Maybe we'll do a slightly different order. We'll, oh, sorry, let me just interrupt for 1 sec. So we skipped over this here. Let's just implement this to kind of prove that we can actually do this. So here we can just do evidence 1 of set, 2, 3. I think that will just work. Okay, sorry, just don't want to like think I was like cheating us there. Okay, so back to union here. Well, so we realized we skipped one thing, which is we actually do need some other set here that we're taking the union with. We can do lots of type level things, but we do need an actual thing to combine with. So we've got these two things we're combining, and then yeah, the union basically kind of does all the work for us. So, I mean, that's simple. Now we still have all the complexity to implement down here, but at least we've got it kind of in one place. So we've got this union thing. And we could start to think a little bit more about like the different cases we have here. So we've got a couple of like easy cases where one or the other is empty. So I think that's kind of just an easy one to start with, and then we'll have a couple of like more complex cases. So we could probably do something like implicit def left empty. And so this is going to take a right. Oh, and this is another one. I'm going to use that without pattern.
Man, and this Copilot is crazy. It gets the types.
Yeah, it's cool, right?
How does it even know where they go? It's so insane.
I think they have slurped up the ZO code base at some point.
Wow.
So the left empty is going to say if the left is empty, and I've got some right, then the union of them is just the right. And the right empty is going to be the other way around.
Oh, I think we transposed the names here.
I was conceptualizing the other way. Of like,
I get you.
Empty. No,
yeah.
no. I mean, it's 6 of one, half dozen of the other.
That makes sense.
And then we've got a little bit of an issue with a situation where they're both empty. So we could either move both of these to a lower priority and have another both empty instance, or we could just prioritize them. So like one fires, then the other fires. Maybe that's an easy thing to do. Okay, so now we've handled the empty cases. So now we've basically got this recursive case. And as we do this, we'll kind of think about some issues we'll run into here. And so this is basically, so I think I'll call it, we have So at this point, we handled all the cases where one or the other are empty. So this case, we can, it's kind of like a pattern match, I guess, in like the value world. We've handled the cases where one or the other is empty. So here we're just dealing with the case where they both have a head and a tail. So I'm gonna start by just giving myself those things. Yeah, this is. Let's see, what is this? Oh, these need to be subtypes of Hsets. Okay, perfect. Okay, so let's just, again, maybe we'll step back to like the H list world, because we know we have this additional complexity of like not wanting to have duplicates, but let's like, first we just got to have a way to combine these at all, we might think. And so basically what we've got to do is we've got to try to eventually reduce this to one of these like base states where the left is empty or the right's empty. And so we can do that by basically, we'll just kind of, I mean, again, just like a list algorithm, we'll like peel off one element at a time from one of them and we'll put it on the other. In this case, because they're these sets where order isn't supposed to matter, it's like a little bit arbitrary whether we kind of like take the left and we put it onto the right, or we take the right and we put it onto the left. I think one thing we may want to think about here is what we're doing with the duplicates and kind of what semantics we want to have here. And so I think probably the most logical thing is going to be, if we think about like left union right, I think we probably want the right values to kind of be the ones that stay in the in case there are conflicts. And so I think that means it's going to be easier for us to take the left values and stick them on to the right, because then we're going to be able to check if they exist in the right, and we'll just basically throw them away if they already exist on the right. And that way we'll end up keeping the right values in the event of duplicates. How does that sound, Kit?
Yeah, I think that sounds good to me. It might be useful exercise to do that thing we kind of mentioned before, which is like maybe have like the value level version of this first to sort of simulate it.
Yeah.
I'm not sure exactly, but it's be something like, I guess, union at the value level, which would be the left, which is a list of A, and then the right, which is a list of A, and then what are you thinking? And then and then of course we want to get back a list of A. So that corresponds to, you know, the left up here, the right here, and then the output is now another Hset.
Yeah, so I think we're basically going to do, you know, a little bit what we've done so far is we've done like left right match. And so we had that left empty case. That was like kind of our first one, right. We said right, and that kind of corresponds to this like left empty case. And then, yeah, we had another, exactly. So we have these two cases. And so now we're kind of, again, in that like left head, left tail, right head. Oh, yes, thank you. Right tail. And so what I'm thinking we'll do here is we'll basically, so let's first ignore like the duplicates problem, but we'll basically do union value of the left tail, and then the left head on the right head on the right tail. And so basically every time we're like peeling one value off of the left and we're making the right bigger and bigger and bigger until eventually we'll have this case and we'll just return this case.
In this case, is it potentially, maybe this is because I can see a value level simplification. Can this turn into a a type level simplification too? Do we need both the right head as well as the right tail in this case, or can we
Yeah,
just
maybe we actually don't. Yeah, well, it's probably
say right?
fair simplification. Yeah. Let's see. I think we might want to keep that just because of the way we've ordered the left empty and the right empty. So we make sure that we eventually terminate by hitting the left empty or the right empty cases. Because otherwise these two are going to conflict with each other.
Oh, yes.
Right. Because eventually.
Oh, will this potentially though solve this problem?
I mean, we can potentially just move it to a lower priority instance.
Would we maybe not even need left empty in that case? Because if we're just doing this right now, if this is anything, then potentially, oh, I see, we want to return. Yeah.
Yeah, I think maybe we can simplify it. Maybe we just stick with this for now.
Okay, totally fine, totally fine. I'll undo this.
Sorry. No, it's a really good thought. So then I think the final thing we need to do here is we need to make sure we don't put these duplicate values in. And so what we could do there is we could say something like if right contains left head. So if the right already has the left head, then we said we want the right to take precedence, so then we can just throw the left head away. And so then we could just immediately go to recursing with union value with the left tail. And and I mean, to your point, we could simplify this, but right now let's just do that. And otherwise we'll keep that and we'll recurse.
Cool.
So I think that's, yeah, we've got kind of, I think, a sound algorithm there. And I think you're right. That's like a really nice way to just kind of get the logic down separately from the type level chicanery part.
Yeah, because it gets all spread out and through these implicit priorities, it could be good to have a map.
So I think just looking at this, it's pretty clear like the left empty and the right empty are going to be pretty trivial. So our focus has really got to be on implementing this recurse. And we also see we've basically got two different cases we want to apply here. We've got where it contains it and where it doesn't. And we've got different cases that, I mean, here are going to result in different types because every different value is a different type in this type world. That's where we're going to want different instances. So here, maybe let's call this maybe we'll call this remove and recurse. And then essentially whenever that exists, we're going to want to do that. So we'll take a second one and we'll call this just recurse down here.
Maybe we'll need multiple levels of prioritization, but we can do that.
Yeah, that's one of the easiest problems to solve, honestly, and if you ever worry about that, just have 20 levels of prioritization. That's really easy way to just solve that problem when you have a bunch of other complexity going on. So this remove and recurse here. So how do we know we want to remove? Well, we said we want to remove when the right contains the left head. And how do we express that at the type level? Well, we've actually already got a tool for that because that was the includes tool we created, which is turning out, I mean, that was useful for reassociation, and now it's coming in for this. And so we can say if and here we can kind of refer down to here because this is helpful. So if the left head is in the right head and the right tail, then we want to do this thing.
So yeah, we can see that calling a value level function at the type level becomes using an implicit of one of these special magic implicits.
Yep. And then we also need this recursive call here. So we're going to need another, yeah, exactly. So this will be a union. And this is going to be a union, but now it only has to handle the left tail and the right head and the right tail. And again, like it's a really great point, like how these things like naturally translate to each other. So there we go.
Yeah,
and
but
then
and instead of match cases, sort of everything, every discrete,
yeah,
a different implicit definition, which is a little wacky, but it's a mechanical translation.
And so this one, we don't need the includes anymore, but we still need the union. And then we've got to fill in the actual return types here. So let's do that. So this one, if we're removing and recursing, then, this, so we definitely, in this case, we know that we've added the right head here, or no, sorry, we have not added the right head here. So yeah, let's go to our little function here. So here we've thrown away the left head, and we're now just unioning these things. So here we should be able to just do union dot out.
Yeah, and I think that makes sense because here we're just
basically returning that
value, and in both cases, yes. So yeah, actually having this map is very, very useful because it can get a little tricky to think through all these, Right. So that's great. And the same thing for the other recurse, I believe, is just we're delegating to this union.
Yeah, I think. Let's see. Oh well, so hold on here. I think hold on a sec, because we still need to return a union in all these cases. Yeah. So, right, because this now knows how to combine a left head and a left tail and a right head and a right tail. And now the type that it outputs is going to be, because we've just thrown this one away, this is going to be union.out. So we still have the union.out. It's just got to appear in that signature and where this. Okay. And I think here, because this union here is just describing the union of the left tail with the right head and right tail, here we need to return left head on the result of the union.
And I wonder actually if maybe this would be more accurately represented at the value level like this.
Yeah.
Yeah, because we mushed it in there. That might actually be.
Yeah.
So this more clearly. Oh, I think it's
I think we've got Okay. All right. So now I think we got everything compiling. We've got all of our union outs. So actually, without even having our implementations, we should be able to just check ourselves here. So we could say, let's see, where do we have some overlaps here? Well, I guess a really simple example would be val union1 is equal to set union set. So this is just the union set with itself. So it should just be set back and check. Yeah.
Now with set 2.
Yep.
Yeah.
String boolean int list string empty. Check.
Let me I'll throw a duplicate in here just to make it make it fancy. There's another boolean, but still only one boolean in the resulting. Yeah.
Only one boolean.
So we set union. Oh my god, amazing.
without actually having implemented anything. So maybe we should do that.
I wonder if we can
again,
use that observation of like, let's see if it. I was curious if it simplifies. Like, can we get rid of the whole?
Yeah,
right
I think we probably can.
Right tail thing, and just have a right where it's right head and right tail.
Yeah. We may just have to be a little more careful with our implicit ordering, but I mean that's definitely doable.
Does that blow things up? Oh, well, one sec. One last one.
Yeah.
Right.
Sweet.
So happy.
Yep.
Still looks happy so far.
Yep. Nice cleanup. Good. All right. Awesome. All right, so yeah, let's actually go and implement some of these. So some of these again are going to be like pretty trivial, and so a lot of it we can just basically follow like the type signatures here. And so like this empty case is, well, if one's empty and the other's a right, then I'm just going to do the right. And here, this will be union.
Cool.
Let's see, are we good? Or I think we got a couple of compilation errors.
Oh, did I screw up here? I might have done that. Oh, is this going to be
Let's-
union.outs, I guess?
well, I think also we usually have to, I think we're going to need this is equal to.
Okay. I guess that we're still missing.
There we go.
Below.
Yeah, we got to do that one below. Yep.
So left head. Wow, this, yeah, it basically can fill it up almost perfectly, which is really impressive.
That's really cool.
And this is going to be, yeah, left head with union.out, which kind of tells us the implementation that we need too. Like, how do we get left head? Well,
yeah, you can tell almost all these are like trivial.
Which has a head, and then we want to join this onto calling union on left, tail, and right. Yay, which is great. And if I move this, oh, I'll just keep the value version there. But yeah.
Yeah, I think we just want to, because we already know. I think we just want to use this one because this is the one that doesn't do the elimination itself because we're already kind of handling the elimination internally. Yeah, we might. I mean, more. I believe. Let's see. Hset.
Oh, and then the friends.
Yeah, I believe so. Let's see.
Was that capitalized? Hset like this?
No, I think that should be lowercase. Because that's just the package. Let's see what the errors we're getting here. And is not a member. Oh, I think we just need.
Value, that is not a member of union out. Oh, do we say it's a, I know we did say it's a type.
We did say, yeah, let's just check our logic here. We said, oh, hold on.
Oh, it's that again.
I think so.
Okay, so it's not a, yeah.
No, it was, yeah, we got some. So wait, left head and left tail, right. Left head and is this not the right?
Union, left tail. Oh, it's left. Oh, that's a union of left tail and right. No, that's correct.
Well, it's interesting that this is not.
Valley is not a member of union.
Yeah, maybe let's just try.
Yeah, try that again.
Take it from the top. So let's see. So this needs to be a new left head, left tail, right.
Type is definitely left head.
Union dot out. Is this? What is this?
Oh, it's still not happy, huh? Just to the type level. Is it this? Oh, it's this type annotation there. Head, tail. It's a weird one.
Yeah.
Maybe I can go back to the right head, right tail thing in this case.
Yeah, I think that might not be a bad idea.
These things are a little sometimes, so this would be, yeah, right head and right tail. And then this would be the union of the right head and right tail. And this would be still union out. Right head, right tail. It's taking a second. Seems to be identical. Oh, here's right down here. So this would be right head, right tail. And this would be right head, right tail. Is it happy? Yes.
Yeah, happy there. Okay. So now it seems to be happy. Okay. So now, yeah. So now I think this, is that right? Let's see. So maybe let's see. Oh, we're doing. So. Yeah, left head. And
I think we want right, just right, right?
Yeah, I believe so.
Okay, good. It's happy. Yeah, sometimes so. The type is
still
a little angry. Oh, it's still sad, huh? Oh, just left.
Left dot head. Left dot head, I think.
Yeah, exactly, left that head. Okay. And
there we go.
Okay, good. Yeah, so
nice. Okay.
You can't make the same refactorings as you can at the value level.
Yeah, sometimes. Okay.
That is a block text. That isn't miraculous. Solid.
So at this point, we've accomplished like all of our let's say 5.5 out of 6 of our design goals for our type level set. The only thing we've half check mark on is the commutativity and associativity because the issue we talked about before. We've also been going quite a while here, so I think we'll try to maybe bring it to a little bit of a conclusion. I want to like put this together to like show like what this could look like with kind of being the environment type, and then we'll kind of call it a day here. So we can imagine, like, let's say we had ZO. And so what would it look like if let's just say we have like flat map here, and we want this to work with this type of, with this like Hset type. So I guess one thing that it kind of pushes us for is like, where does this exist? Like, it's a little bit of the same question we have with ZO of like, right now the R can be anything, but like we really like typically want it to be has unless it's any. So there's a little bit of design question here of like, would you just say like the R always had to be a subtype of an Hset, and then just like any would be like the empty Hset? Or would you kind of try to do that as more of like an extension method type thing? I think the other thing we're going to get pushed into a little bit, let me just illustrate this for a sec. So we could say that, well, like R has to be a subtype of Hset. And then we could do something like R1 has to be a subtype of Hset. We'll have E1, we'll have B. We'll say you can do some function to ZO R1 E1B. And then you'll get back a ZO. And so in this world, we'll then say, you've got to have this union. That's a union of R and R1. And then this would become like union.out, E1, B, question mark. And we get into a little bit of an issue with variance here, because this union type right now is invariant and R is contravariant. And in fact, if we look at union, we can kind of make it contravariant if we want to, because these lefts and rights are really inputs. But that actually doesn't help solve the problem. That just makes it the other makes there's covariant versus contravariant instead of invariant versus contravariant. So it seems like when we go this way, we kind of get pushed to do this more as like implicit syntax. So we could do something like implicit final class hset ops. And so then this will have the like R is a subtype of hset EA, self, ZO, REA, anymo. And so then we can kind of remove this constraint here, which maybe is nice because it lets us kind of keep ZO itself as fully general. And then this flat map thing will come in here. And now I'll just get rid of, I'll reverse what I did with the unions. Where's my union? Where's my union? Oh, I think I did that. Oh, it's happy now. Sorry, it was a delayed reaction on the compilation there. So now this is kind of going to work. And so if I can do that, then you can imagine I have something like, let me do like trait database, trait logging. Maybe I'll do one more. I'll do like whatever, trait monitoring. And so ZO1 is going to be a ZO that uses, say, a database and nothing else. And maybe this can't fail. And right now it's going to be very boring. So it's going to give us an int. And the next one, yeah, we'll use logging and monitoring. And then we'll say val ZO3 is equal to ZO1 dot flat map. And right now I'm just going to do very boring things with it, just so we can kind of this. That's this needs an age empty, right?
Yep. Yay.
Okay. And so this compiles, and I mean, this definitely has its coolness, right? If I just, that's weird. All right, so I don't know if that was, oh, sorry, I'm throwing off your buffer.
Oh, the undo.
Yeah, so let's see. So it's interesting because when I hover over here, I get exactly the right type. I don't know if it's just because there we go. I think maybe we were just like in process.
Yeah, exactly.
But so like this got exactly the right types, right? It got all of them. It properly handled the duplicates. So that's kind of cool. I guess one interesting experiment could be, will this kind of reversing the order work? I'm not sure if it will or not. Survey says no. So that's where that like commutativity identity thing falls down a little bit. So, point in favor of current encoding, but, interesting to explore that stuff. Maybe there's something we could do with like implicits of like, if you have a like isomorphism, you can like lift it into a context. Maybe it could be solvable, but I think kind of shows that like, that's going to be a continuing thing that's going to require work to like deal with. But this is overall pretty cool. And the other thing that's kind of interesting is we could imagine supporting other operations with this. So like we could imagine an operation that lets us eliminate a type. So maybe we can even do that. Say we had something that's like provide sum R1. R1 is going to be an R1. And let's say I have an implicit eliminate for R1 and R. And that's going to give me, implicit eliminate, yeah, thank you. Mm-hmm. And that's going to give me eliminate dot out. And it'll just keep the same E and the A. See if that's happy. Okay, so then I'll sample database. So now let me do, let's do val ZO4 is equal to ZO1 dot provide some sample database.
It works.
And look at that. We like eliminated the environment. So I mean, again, like other we could definitely like point to disadvantages, like the fact that like that didn't work when we reversed the order, and like the fact that we've got these like H empties around is not great. The fact that we had to move all these things to implicit syntax is not great. The fact that like basically like every like R signature ever is going to have this like union thing is like not great. So like, yeah, there are definitely reasons why we got where we got, but like this like ability to partially eliminate the environment and like not having to specify type parameters for it, this is, you could say, was kind of like the holy grail, I feel like, that we've kind of been exploring with like ZLayer and like haven't gotten to. So yeah, there's also something to be said for that. So yeah, I mean, I think we're at past the 2-hour mark here, so definitely time for conclusion. But hopefully, I mean, one, you kind of saw like this like type level stuff is like, you know, not magic, that like you can do it too, we can all do it, and it can be fun. It's definitely like its own thing that, you know, maybe don't do at the same time you're trying to solve a production issue, but if you got like an afternoon, it's like, you know, cool, like little learning experience you can do. Hopefully you learn some about doing it yourself, and yeah, hopefully you kind of saw something about this you know, interesting alternative design that we explored at one point for a pretty important part of ZO, and some of the trade-offs involved.
Yeah, that's very cool. Thanks, Adam. And
yeah, do we have any questions, or have we or do we have any viewers left? Might be a better question.
Yeah, we got a few viewers. Will the code and the recording be will the code and recording be available? Yes, both will be available.
Definitely. Yeah.
Adam, maybe if you upload this to a gist or something, we can post it on the Discord, which I will send a link to those in the chat. Usually we try to chat in the Discord just to consolidate the chats. And I'm always bad at finding the link. Where is the link? Is it?
Yeah, I'll paste it again. Let me grab it.
Okay, gotcha. Oh, we have to right click on the name. I see.
Cool. Yeah, I'm always just, I'm gonna stop my share.
Yeah, I pasted it in the, so yeah, I pasted it in the.
Oh, you got it? Okay, perfect.
Figured it out.
Okay, great. All right, cool.
Okay, awesome.